Millikan's oil drop experiment. Do you know how scientists measure the tiny charge on a single electron? This is Millikan's oil drop experiment, one of the most elegant experiments in physics. Using charged oil droplets and an electric field, Millikans made these droplets float in the air. Introduction. Millikan's oil drop experiment is used to determine the charge of an electron, a fundamental constant in nature. Experimental setup. Here you have a highly evacuated chamber. There are two plates A and B. The two plates are given high potential difference and there is a electric field maintained between plate A and B. The potential can be adjusted, thereby the electric field can be adjusted. There is an atomizer. This sprays the oil droplets over the chamber. Through a hole it enters. And there is another hole in the plate A through which every drop can be filtered. There is an opening on the right through which these oil droplets can be viewed with a microscope. There is another opening on the left hand side through which light can be sent to illuminate these oil droplets so that these oil droplets can be more visible. Two parallel metal plates A and B. These are having diameters approximately 20 centimeter and the gap between the two plates is 1.5 centimeter approximately. A high voltage, approximately 10,000 volt is applied across the plates. The electric field acts downwards. Oil drops, non-volatile, are sprayed through a hole in the top plate. Some oil drops get negatively charged due to air friction or X-rays. Light illuminates the drops. Microscope used to view their motion. When the electric field is turned off, droplets falls under gravity and reach terminal velocity. With this, we calculate the radius of the drop. When electric field is off, drops fall under gravity with the terminal velocity v. Here you have a magnified oil drop. Let us find what are all the forces acting on it. A downward force Fg, this is weight of the droplet. A buoyant force Fb, which acts upward. The motion is downward with a constant velocity called terminal velocity v. Thereby, by Stokes' law, there is an upward viscous force we call Fv. Forces Fg is the weight mg, mass is replaced by density multiplied by volume. So we get rho times 4 by 3 pi r cube g, weight of the oil drop. M is the mass of the oil. G is the acceleration due to gravity. And rho is the density of the oil. And r is the radius of the oil droplet. The second force, Fb, the buoyant force, the upthrust on the droplet. This is equal to weight of the air displaced by the oil droplet. So, Fb equals sigma times 4 by 3 pi r cube g. Here, sigma is the density of the air. The third force is viscous force by Stokes' law equals 6 pi r v eta. Here, v is the terminal velocity and eta is the viscosity of air. Let us subtract the buoyant force from the weight. So we get an apparent weight equals Fg minus Fb. In the balance force, Fg minus Fb equals the Stokes viscous force Fv. The apparent weight Fg minus Fb equals 4 by 3 pi r cube rho minus sigma times g. Viscous force Fv equals 6 pi r v eta. So, force balance is apparent weight Fg minus Fb equals the viscous force Fv. Instead of the apparent weight, let us write 4 by 3 pi r cube rho minus sigma g equals 6 pi r v eta. On solving for radius r, we get r equals square root of 9 times eta v divided by 2 times rho minus sigma times g. So r equals square root of 9 times eta v divided by 2 times rho minus sigma times g. Now turn the electric field on. A particular drop can be held still by adjusting the voltage. With this, we can calculate the charge of the electron. When electric field is on, drop is suspended. Electric force balances gravitational and buoyant force. Through the opening, let us send X-rays so that air is ionized. From the air, few electrons stuck with the oil droplets. Let us illuminate again the oil droplet to view. The magnified oil droplet is taken and let us know what are the forces acting on it. The downward apparent weight Fg minus Fb and an upward electrical force Fe. Here the oil droplet is at rest, so the viscous force is 0. Force balance. The electrical force Fe equals the apparent weight Fg minus Fb. Let us substitute the electric force Fe as Q times E and the apparent weight as 4 by 3 pi r cube rho minus sigma times g. From this formula, let us find Q. Q equals 4 divided by 3 times E multiply pi r cube within bracket rho minus sigma multiply g. Then Q equals 4 divided by 3E multiply pi, then 9 times eta v divided by 2 times rho minus sigma times g whole to the power of 3 by 2 multiply rho minus sigma times g. When we simplify this formula, we get Q equals 18 times pi divided by E square root of eta cube v cube divided by 2 times rho minus sigma times g. So the final result Q equals 18 times pi divided by E square root of eta cube v cube divided by 2 times rho minus sigma times g. Millikan repeated the experiment and always found that oil drop charges are multiples of 1.6 multiplied 10 power minus 19 coulomb. This value is the charge of an electron. E.